US low carbon liquid fuel production using hydrogen enhanced biomass or MSW gasification. MSW stands for municipal solid waste. Yeah. So to give an overview of the talk, I will talk about biomass to liquid process. Then I will move on to talk about potential hydrogen enhancement of biomass or MSW to liquid fuel, which can increase the production of the fuel by a factor of 2. Then I will touch upon the potential production of biofuel in the US based on the billion-ton DOE report. A bit of motivation for our work. Low-carbon liquid fuels are needed for key transportation sectors and other difficult to electrify sectors. Biomass or MSW gasification to liquid fuel is one of the promising pathways to produce low-carbon fuels. Conventional biomass to liquid processes have low carbon conversion efficiency due to hydrogen deficiency in biomass or MSW. And carbon conversion efficiency is important because there is limited amount of biomass. Our focus in this work is on production of methanol. It's one of the easiest and most efficiently produced fuels from synthesis gas. It can be used as a fuel by itself or converted to gasoline, sustainable aviation fuel, or SAF, and other fuels. It can also be used for a variety of chemicals. A brief look at the conventional biomass to liquid process. Biomass is gasified in a gasifier, and then we produce syngas from the gasification, but that syngas has low hydrogen content. So what is conventionally done is to increase that hydrogen content by water-gas shift reaction. With water-gas shift reaction, we shift part of the CO together with added steam to hydrogen and CO2. But the downside is that that CO2 is a carbon loss, and that needs to be taken out from the process. And that's the reason for more than 50% of the inlet carbon, which is lost as CO2. What we can do to improve this carbon efficiency is to add externally sourced hydrogen to the biomass to liquid process. This we call hydrogen enhancement of the gasification to methanol process. It's important that the hydrogen be sourced from low carbon sources, and we have looked at hydrogen production through electrolysis and natural gas pyrolysis. We have chosen solid oxide electrolysis for production of hydrogen, which has advantages because of availability of high temperature heat after the gasifier. Pyrolytic conversion of natural gas is a promising technology and can potentially produce lower cost hydrogen. We have done this analysis based on in-train flow gasification and multimedia units for the pyrolysis. And the results of this study is published in this paper. As I mentioned, natural gas pyrolysis for production of hydrogen can potentially produce cheaper hydrogen than electrolysis. In order to integrate this way of producing hydrogen, we have developed a framework where we integrated the natural gas pyrolysis to the biomass to methanol process. We looked at 5 different integration options and with techno-economic and life cycle analysis of this framework. And the results are also published in this paper. Like biomass, we can also convert the municipal solid waste to fuel, to methanol by hydrogen enhancement. And in this slide, I'm showing the total life cycle GHG emissions of this hydrogen to fuel process, biomass to fuel with hydrogen enhancement process. On the x-axis, we have the total GHG emissions in kilogram CO2 equivalent per ton of produced methanol. And on the x-axis, we have MSW gasification with electrolytic hydrogen and pyrolytic hydrogen. And it's important to note that we assume a renewable electricity and 20-year global warming potential of, for the methane. And the results show that we can have negative life cycle greenhouse gas emissions by conversion of MSW to fuel with hydrogen enhancement. One of the main reasons is the landfill methane avoidance by not landfilling the MSW. And for the pyrolytic conversion of the hydrogen, it's important to note the fugitive emissions in the natural gas supply chain. So here we vary the fugitive emissions of natural gas supply chain from 0.2% to 4%, and we saw the impact on the total life cycle GHG emissions of the fuel, which is shown. The net GHG emissions are represented by solid black bars. So it's, the takeaway message from here is that fugitive natural gas emissions has a great impact on the total life cycle GHG emissions. So far I presented the hydrogen enhanced biomass or MSW to liquid process, and we want now to look at the bigger picture and see how it impacts the total potential of US low carbon liquid fuel production. Based on the billion-ton report by DOE in 2023, they predict future additional production capacity of more than 1 billion ton per year of biomass. And also the report states that this has potential for production of 60 billion gallons of sustainable aviation fuel per year. And we believe that with the hydrogen enhancement of biomass or MSW to fuel, this might potentially increase to 120 billion gallons of SAF per year. So we double the production hydrogen enhancement, but that requires availability of low carbon hydrogen. So as I mentioned, one way to produce low carbon hydrogen is through pyrolytic production of hydrogen, and for that we need natural gas. So here in this figure we show we see the natural gas pipelines. There are abundant reserves in the US with extensive pipeline network that spans the country. So and we see large overlap biomass and MSW production sites in eastern and middle US. For electrolytic production of hydrogen, we need renewable electricity, and one way to get renewable electricity is solar and wind. So here I'm showing the solar potential and wind potential in the US. So our next task would be to overlay these maps, natural gas, biomass, and solar and wind potentials to find the suitable locations for hydrogen enhancement of biomass or MSW to fuel. So to wrap up my presentation, some key takeaways: hydrogen enhanced biomass or MSW, gasification to methanol or other liquid fuels could provide a range of possibilities for substantially increasing the production of biofuels in the US. On one end of the spectrum, it could provide additional certainty of reaching the 60 billion gallons of SAF per year, which was reported in billion-ton report by DOE. On the other hand, and most optimistic end, it could potentially enable the production of 120 billion gallons of SAF per year. MSW conversion to fuel has the dual advantage of both avoidance of landfill methane generation and production of low carbon fuel. As I mentioned, the next step would be to overlay these maps to find the most suitable locations for production of low carbon fuels with hydrogen enhanced. Thank you for your attention.
We have time for questions.
Yeah, thank you so much for your talk. I have a quick question regarding the hydrogen enhancement approach. Have you compared how much is the price difference if you compare to the conventional way? Because for hydrogen enhancement, for example, you need to add, for example, the electrolyzer, but for the conventional way, you have the air separation unit, so a trade-off between conventional and enhancement way.
Yeah, we have done that in this paper, and that's a very good question. It depends on the capital cost of the electrolyzer and the electricity cost. Electricity cost is a very important factor when we want to compare the benefit of or the levelized cost of hydrogen enhanced fuel compared to conventional BTL. But at low electricity price and also optimistic cost of electrolyzer, hydrogen enhanced fuel can be cheaper than conventional BTL, with the advantage of that we need less biomass for the same output, or half of it, yeah. Especially when biomass resources become scarce. So with hydrogen enhancement, we solve that problem as well.
Any other?
So for this one, for your hydrogen enhancement, why you are consider about two hydrogen resources? One is from the water electrolyte and another from the pyrolysis.
Yeah.
So what's the reason about choosing two hydrogen?
So here we were thinking about having a flexible process. Just when electricity, for example, is very expensive or unavailable, then the natural gas pyrolysis can act as a swing, so it can we can turn it on and off when electricity is scarce for SOEC. So we wanted to have a flexible hydrogen addition to the process.
So over there.
Just a follow-up to this question. So that would mean that you would also need the ASU installed on site, because if you're doing a flexible process, you need the oxygen.
Yes.
Any last question? Go ahead.
Yeah, another question. I guess for this process, you were going to the chemical grade methanol, right? So because we have seen also a lot for like marine applications that you can have like lower purity methanol like at 90%. So we wonder how the analysis of methanol that you have done will change if you consider having lower purity standard for
Yeah.
the product.
Yeah, your question deals with this part, product purification. So our distillation columns would be easier because we need less purity of methanol. So that would be easier. Yeah, if you want 90% compared to 99.9%, then only the distillation, the end step would be different.
Any question? Now let's move on next.
Our third speaker today is Professor Tae-Suk Moon.